Shall we go ahead?
Yes, sir.
Sure. Thank you, Diksha. So, very good evening, everyone. As we know that this is the second half of the day, so everyone, few of them may be tired. So I don't want to be keep this like a traditional lectures or delivering like I just present all these things, because nowadays in LLM generative AIs and all those things, if you type simply just this heading also, you will get lot of materials. So I would like this session more on discussion, right? And whatever you have in your mind or wondering the questions related to that, more practicals or the basics or whatever, so please don't hesitate, and you can ask anything related to CNN or neural network, right? So I want to be this lecture more brainstorming rather than just this uh, you know just a simple lectures, right? So I have switched off my camera so we can present. So if anyone interested in asking the questions before that, or have any specific questions, please ask. Otherwise, we will start,
Sure, sir. Sure, sir.
right? So I think as we knew that this is the third day of this workshop or a conference. So all of us, I think, related to the CNN or deep learning modules have some idea related to that. But before start this discussion, I would like to give just a brief introduction about the neural networks and their shortcomings and why we need, the CNN. So as I expect all of aware of this what CNN is. So as we know that this is like a line, the tagline of deep learning. uh, ANN is new, based on or inspired by the human brain, not exactly the human brain is more complex, and has a very large billion of neurons and all. But in the ANN try to mimic that. So like as the neurons receive the input from the dendrite and activate their signals, based on that human brain make a decisions. So similarly, at a very small level, why I'm saying the small level, because in human brain, as I mentioned, billion of neurons, but here we deal with a limited number of neurons, and try to mimic and make the art decisions based on this limited number of neurons, right? So it has the similar layer, input layers, where input layer is very simple, like how many input features we have in our data set. So let's say we have a data set of human body weights and height. So x1, let's say, represent the weights, and x2 represent the height, right? And these passes to the hidden layer. In hidden layer, these number of neurons could be anything. It's based on our architectures and depends on this how these neurons impact or effect. So we introduce the weights and bias in between the one layer to another layer, next layer, right? So here first layer is input layer, how these neurons flow and information flow one layer to another layer through weights and bias, right? And similarly, in between the hidden layer to output layer, we have another set of weights and wires. Through that, this information finally reach up to the output layer. Here, this is just a diagram for just an examples, schematic diagrams. But in real, these hidden layers is not a single layer. It could be, 20, 30, 50, up to 100. So usually, real pipeline or architectures has hundreds of hidden layers in between, right? We'll discuss in the tomorrow lectures, or tomorrow discussion in the classification and object detections part. So the real network. But you can assume or visualize these things. So hidden layer is not a single layer. These are the set of layers, which could be 10, 20, 50, or hundreds, right? So this is the basic, but as we can see here, we are directly applying these inputs, x1, x1. Oh, it should be x2, right? Second one. So x1, x2, x3, xn, directly replicating and applying the weights over that. So these are the few limitations, because if we have the inputs, let's say 1 lakh inputs, right? So to process these 1 lakh inputs with the weight and multiply that, it will be very difficult to maintain all these things. So ANN struggle with handling the high dimensional data, like image especially. I will explain how the image is very high dimension data. So it could not handle this. Second, as we can see in this also, it's quite a flat structures. Whatever we are feeding to our network is x1, x2, xn form. So although image has this architectures and we can say the space and dimensions like channel and neighborhood information also play a critical role in applying any operations, classification, or we can say the object detections and all. So that's why it is not suitable for image, right? One is computation, second is hierarchical structure itself. So to overcome these shortcomings, CNN, has been introduced, and researcher feel a need of a new algorithm which can overcome these two shortcomings and successfully handle these image kind of data. So CNN can handle the image, others kind of data as well, where the dimension of the input is very very high, right? So how they tackle these things? It has the 6 basic components, as we can see in the image as well, and we have written the A. So first is the convolution, then activation layer, then pulling, flatten out, fully connected layer, and output. So one by one we will discuss in this. This discussion is around all these 6 components of that. As we can see in the this diagram, this is again a schematic diagram of just a classification to just give a glimpse or idea how it works. So let's say we have an image, image, and apply the convolution functions on that, then activation function, then pulling. So it will be a sequence. But again, here we just show the 2 convolutions and 2 pulling, but it will be a set of these convolutions and pullings, and usually range in between 50 to 100 or 150 as well. Deeper network, goes up to a 150 layers as well, right? Later part, the fully connected layer is just simply like a neural network layer. And then finally, we have our objective functions. We sometimes call it a loss functions. We'll discuss. So this whole discussion is around these 6 components. So let's start with the convolution. So this is the basic of the convolution. That's why its name is CNN, convolution neural networks. So when we get the image, right? So as we can see this car image, part of the car. So we have height and width and channel, right? So usually in the color image, we have a 3 channel RGB, red, green, or blue, correct? And with this combination of that, it's become an image with different colors. We can see that. So convolution we can visualize, not mathematically correct, but to understand just like a magnifying glass, and we are sliding on the objects, means the image, and try to find out or look out what is the pattern. We can find textures and corner in that image, right? So convolution work like a zoom in the image and find the minute textures, colors, edges, corners in the image, which can use for later operations. So that is the basic of convolutions. So if we go to the mathematics, like how it performed like this. So this is like this. RGB, there are the 3 channel, as we can see in the GIF image, and we overlay this convolution function, or we can say kernel over that image, and try to extract the relevant features. So relevant features means It may be edges, it may be a textures, it may be a pattern or colors as well. So because every pixel says the, so before moving forward, everyone have some idea about the image, or should I explain about image as well? If anyone don't have, please let me know. Otherwise, there is no point. I will move forward and you just see the numbers and all.
Please explain.
Okay. So how the image is formed? So image is a combination of, let's say, I move to the back slide. Yeah. So as here we are depicting this car image, right? So it's not a single matrix. It is a matrix of, let's say this image is simply, I say 256 by 256 size, right? Height and width of the image, correct? So it's not a we are seeing this as a single image, but it is a combination of 3 channel, and each channel has the values of 0 to 255, right? So R means a red channel also has the 0 to 255, and green and blue also has this pixels. So when we say about height and width, means these have just visualized as a matrix, and which has the 256 columns, 256 rows, and each cell has some values, right? And these values would be in between 0 to 255. For simplicity, I am saying this, right? So it form these, combine these 3 channel, form the image, right? So all these operations, that's why in that GIF as well, you can see the 3 slice: blue, green, and red. And when we are applying this or overlaying this convolution network, convolution function over that, so you can see finally we are getting the results of this bricks kind of things, means a slice, which would be the combination of 3 channels, right? If we see the top right image, for simplicity, we are depicting the single channel image. So let's say this green, this pink and white is the exact our input image, and this blue and light blue is our kernel. Kernel is nothing but the matrix of any size. But for mathematical and the function, characteristic, we usually take a odd dimension, like 3 by 3, 5 by 5, 7 by 7, right? To keep it the neighbor information as well of this image. As we earlier discussed in the first slide, why the neural network failed, because each image had its uh, space, we can say the special features as well. That's why we are taking this odd dimension, right? So I will discuss more mathematically, which help us to understand how it performs. So let's say we have this image, and this is the mathematical function Si and J. It's represent I is the image, K is the convolution kernel. Kernel is, you can see I represent this, uh, you know 5 by 5 image, and kernel is nothing but a simple matrix, right? And as previous slide we have discussed, 3 by 3, 5 by 5. So here for simplicity, I just have considered the 3 by 3 kernels, which has 0 1 0 1 values, 0 1 0. So how we apply this convolution? This is the image, let's say in the figure or diagram this. So we put this filter on the image at the very first place, right? So 1 1 0 1 0 0, and we apply this S11 formula, nothing but the simple point-wise multiplication. So 1 multiplied by 1 plus 1 multiplied by 0, you can see that 1 multiplied by 1 again, 1 and 1 you can see, and adding all these multiplications, and you can get a 3, first row, first column. Similarly, if we put on the 1 1 1 1 place, means shift these kernel towards right by 1. When we say the stride is 1, just slide by 1, right? So you will multiply that, and similarly you will get the value of 2, right? So by similar this mathematical formula, if we apply, it is nothing but the point-wise multiplication and addition of the image and kernel or filters, right? Addition of this, we will get these values. So for more clarity, we can see this. Here, I try to, replicate the image of RGB channel. So first would be the, channel 1, 2, and 3. And these are the kernels. So for simplicity in the first slide, the previous slide, we have just shown the 3 by 3 kernels. But actually, kernel would be also 3 by 3 by 3, right? Height, width, and number of channels. So always, the traditional kernels or filters, we can say, would be the equal dimension of the number of channels in the image. We can, make the change in that, but usually the size of the kernels would be equal to the number of channels in the image. So as we can see in the RGB, we have the 3 channels, and so the kernel also have the 3 channels, and dimension could be anything. Right here we have taken the 3 by 3. So as you can see, the final output of that, we apply the 2 kernels over that, and we get the 2 different output, right? 233, 373, 38 minus 3, right? And if we apply the second kernel W1 with the different weights, so we will get a different matrices, right? So how it affect the things, and what would be the happen later, I will show the result as well for the similar kernels. So till now we have discussed this simple kernel, widthwise kernel we call it. If we want to improve or enhance the kernel or convolution capabilities, so till now, as we discussed, we just considering 3 by 3 into 3, means the number of channels and for each image. But if someone want to extend the similar convolution networks or CNN for 3D or for videos, so introduce one more channel or one more, we can say the dimension, that would be the number of frames, or we can say the number of images. So till now we have just considered height, width, and number of channel. Here we also include adding one dimension, number of frames, or we can say the number of image. So as we can see, the few image from the medicals and others have the 3D dimensions also, right? So it is nothing but the simple extension of the convolutions, right? We add one more dimension. So as in the image you can see, instead of just flatten 3 by 3 into 3 kernels, now it's see it look like a cube, right? Which has 3 channel, and which also has the number of images, right? And finally when we apply, it will give the results also in form of the cubes. Another kind of convolution is, as we discussed, it has only a 1 by 1 dimension. So height is also 1, width also 1, but number of channels could be anything, right? As we can see here, 1 by 1 into n, right? It call it point-wise convolutions. So these are just 2-3 type of convolutions. More depth is also similar kind of convolutions. So you can explore others as well, and how they different from each other, we will discuss in that slides. So this is the summarization of all kind of popular kind of convolution functions. We can say 2D is the traditional and most popular convolution. 3D is a convolution, as I say, extended dimension or extension of 2D convolutions. Depth wise is slightly different. I want to give you the few details related to that. When we apply, and we will see more in the mathematical comparison, but as we here we can see, in depth wise, what we are doing, instead of applying directly 3 by 3 kernels on the image, we are separate out separate into 2 functions. One is depth-wise convolution, second is point-wise convolutions, and combine those, these two convolution functions. By doing that, we will able to reduce the time complexity. We can say the computation is less as compared to applying the traditional, or we can say the width-wise kernel convolutions, we can say, right? How it will reduce the dimension, we will see in the mathematical formulation. So this is the basic summarization of these popular kind of convolutions. So if we see the mathematics of convolution, let's we have an image of height h, width w, and we have a kernel of height kh and width kw. Padding is something, if we are applying the convolutions on the image and dimension is reduced, so we add the columns or rows with 0 or 1, we call it padding, to keep the dimension of the image is to maintain the dimension of the image, or whatever dimension you want finally after applying the convolutions. Because when we apply the convolution over the image, the dimension would change. So final dimension after applying the convolution is changed, slightly changed, as we see here. Here we have a 7 by 7 image and 3 by 3 kernels. So finally, what would be the output is 3 by 3, right? Everyone clear here? If someone has doubt how it applied and what's going on here, please ask the questions. Great, everyone is clear about these operations, so we'll move forward to that. So what would be the final dimension applying this formula? What would be the final dimension of h dash applying this? So let's say we are applying we have an image of 32 by 32 and applying the filter of 5 by 5 with strike 2 and padding 1. So final dimension would be 16 by 16. If we apply there also 5 by 5 into 3 by 3. So similar formula, we will get a 3 by 3 image finally, right? And similarly, on the width of that, it's similar formula because it is a, symmetric operations. So we will finally get a 16 by 16 image output. So as we discuss why the people feel depth-wise convolution is needed, if we see how many multiplication or computation is needed in applying the simple normal convolution. So let's say we have the height and width and channel, right? H, W, and C, and we apply the kernel with height, width, and channels. So multiply all these things. That would be the multiplication operations we need to find the final output, right? So if we have an image of 25 into 25 into 3 channels and 2 filter applying 5 into 5 into 3, so what would be the cost? You can see that also the reason we can not directly applying the ANN on image data, right? And if we applying the normal convolution, you can see 66,150 mathematical operations and additions we needed. But on the similar size of image and similar size of kernels, we apply through the depth-wise convolutions. Now you can see, because in depth-wise convolution, height, number of channels is not involved here, C dash, right? And in the point-wise convolution, we have no height and width because these are 1 by 1, if you remember, right? Height and width of a point-wise kernel convolution only 1 into 1. So you can see the total computation of depth-wise convolution plus point-wise convolution. adding both these computations, we will get these numbers. So which is less than half, approximately half of the normal convolution operations. So computationally, to make our, CNN computationally efficient, we need this pointwise convolution. If we discuss about the performance of that, it is in various research papers or practical operations and applications as well. It has been proven it has more or less similar accuracy. So on the effectiveness, we can say, or performance wise, its accuracy wise is slightly comparable. In few cases, it has been observed performance is reduced by few percent in the point, actually, not the percent. It will after a decimal point, right? So that's why in the many networks, especially a mobile networks, which developed for, lighter application and run on a mobile devices or your local system, preferred this depth-wise convolution. Any question till here? Because we summarize this first, the major operation convolutions operations in CNN. So convolution is the base of, that's why it's name of CNN. So if someone has doubt on up to till here, please ask. Don't hesitate. As initially I pointed out, don't make this like a lecture. It would be, I preferred more on discussion. Okay, so we'll move forward.
Hello,
Yeah.
sir. Am I audible?
Yes.
Sir, I would just want to ask that, uh, like we select the kernel size. So will it depend on the task or the kind of image data set that we have? How we can decide that what will be the kernel size?
Okay. So usually, as earlier I have mentioned in the first slide, right? So it would be the size decide on the 2-3 factors, right? First, why we are taking the outside 3 by 3 is the reason being because, as we can see in the image, is a structural and space, right? Structures means never of the pixels is also matters, right? If we see the event dimensions, in that we can miss that information, so we prefer the odd dimension, right? Now the second question come to the dimension. People experiment on the different dimensions, like the most popular is 3 by 3 kernels, also experiment 5 by 5 and 7 by 7. If we increase the size of the kernels, there is a chance we start missing the minor information, right? As we have seen, it is a point-wise multiplication and combination of these, kernels and image, correct? So according to that, ideally it will not affect, but if we increase the size much, it may impact on whatever the features we are extracting, right? So we have a reasonable size. So people preferred 5, in between 5 to 7 dimensions, right? You got your answer, or you have
Yes, yes, yes,
more?
yes. Thank you so much, sir.
Any other questions? Okay, so now move to the activation layer. So once we apply this convolution, so as we observed and seen, it is simply a mathematical operation, right? We multiply point-wise multiplication, perform the addition, and we'll get some numbers, right? And it's a linear operation, because we multiplying x into x1 into w1 plus x2 into w, any weight matrix or weight vectors. So which pixels contributing in our feature extractions, or which would not be so useful, how we will decide that? So filter out few noise, we can say. Noise is would not be the right word. We can say the few less important pixels, and just keep it a few important pixels or data from the after applying this convolution operations. We introduce activation layers. It is here we apply some non-linear function, and which help us introducing the non-linearity as well. So we can also extract the features and introduce the non-linearity in our models. Otherwise CNN will work like a if everyone is aware of this, like a simple linear model, like the linear model, we can say ridge regressions, or this kind of linear functions, and can be represented in a single layer, because which would be x1 into w1 into w2 into w3. So to avoid that collapse into the linear equations, we introduce the non-linearity activation functions.
Say your slides are not moving actually.
Now
Yes, sir. We are stuck on 16 slide.
16, now it's 17. I am at 17 activation layer. Now moving.
No, sir.
What happened? Let me check here. Oh,
Now we are on 19th.
yeah. Yeah. Now we can see.
Yes, sir. But can you show it in full screen?
Yeah, it's a full screen. I am in the presentation mode. Now you can see. But there is some delay due to this network or something. Now you can see.
No, sir. It's not in full screen mode.
What happened? Was now.
It's slash 17.
Sir,
Here the message
you may
actually.
share it as an entire screen, sir. Then because you may share the only one PPT, so it's changing on the PPT mode itself, not in slideshow.
One second. No, I have shared deliberately only this slide, because otherwise lot of, if I share the entire screen, it may be,
Then only we will get a slideshow, sir. Otherwise, we will
yeah.
use only PPT.
Okay.
Now it's visible.
Yes, sir. Now we are good, sir.
Okay, great. So now you can see that, right? So it's again, okay, I just repeat about the activation layers. So activation functions and activation layers. So after applying, as earlier we see the image of this car and applying this convolutions. So it is again the schematic diagram just to show and examples, right? So if we apply the activation and non-linear function over there, so we will get the result like this. It's not the absolute results, but just to depict the effect of the activation layer. Earlier, when we apply the convolution, it will be like a red kind of image, right? Blur kind of image, but we can see the few edges and other things. Here, if we apply, we can see the more clear edges and the features. So it will be like this, right? Also help to introduce the non-linearity in our networks, and only selective inputs, which we call neurons, fired if they pass through the activation layers, and also clear the threshold. So different kind of functions we use, and has the different threshold as well. So this is again just an examples of this, how the linear and non-linear networks is, distinguished to each others. You can see the left one is the linear, and right one is the non-linear functions, right? So difference, you know we can visually also observe and see what would be the difference if we introduce the non-linearity. So when we say about the activation functions, it's a simple linear combination of non-linear functions, but it should also uh, you know follow some mathematical characteristics, right? So usually prefer those functions would be smooth mathematically. We can continuity, we can check, and also uh, you know uh, also compute the derivative differentiable means, we can say simply. So everyone has the mathematics I think lectures also, or discussion before that, correct? So everyone is aware about the continuity and differentiability, all these mathematical characteristics of any function. If someone has question related to that, please ask, otherwise miss the next few slides. Okay. So I assume everyone is aware related to that. Okay. So these are the popular mathematical, we can say the activation functions. The most popular is ReLU, rectified linear unit. It's a simplest but most popular activation function. It is simply max of 0 and x. Means if the values after convolution is 0, uh, greater than 0, it will remain same. Otherwise, if it is negative or 0 less than 0, it will make it 0. So it simply we can say the ReLU will not allow any negative values, right? So it will always greater than or equal to 0. So advantage of this, it's a simple mathematically. If we see all the operations till now, we see convolution is also very simple. If we see, right, just point-wise multiplication and addition operation. And as you can see, it is also very simple operation. If some value is negative, make it 0, otherwise remain the same. Correct? Second is slightly complicated. It seems like more mathematics, and completely a non-linear shape is S-shape function and sigmoid function. And we heard about all it's one of the most popular and used earlier. Nowadays is slightly less compared to the ReLU activation function. The mathematical function, you can see 1 upon 1 plus exponential of minus x, but and it would be a S-shape function. Will show you this kind of function, right? S-shape. So if we put the value of x anything, it will always in between 0 to 1, and as we increase the value, it will go linear and linear on the positive side as well, on the negative side as well. In between, it is the slope is slightly higher, so it will also use in other cases as well, like classification, activation, and all. 10H also has slightly more slope and more flatten out near to 0 and near to 1 and near to -1. So ReLU is like this, as I explained. ReLU is like, if it is greater than 0, remains same. If it is less than 0, always we are 0, right? Leaky ReLU, and just keep in mind these two graph as well. Why we use it? Because at the 0, that's why I ask, it is slightly not differentiable at exactly a 0, because a corner is there, right? So we face some difficulties. Also, it will not allow a negative values. So few researchers do the exploration regarding that, and see the impact, how this non-negative only domain, how and range, how this function affect on our final results. So it has been found If we allow slight negative, not exactly, the exact negative, but slightly, right? So it will help in few cases, not all the cases, but in few cases it helps, and make it slightly like ELU. If you see the similar kind of thing, that is more smoother than this ReLU functions. So these are mathematical reasons behind these two, and those help in the few cases, also help in the computation. But if you see the ReLU in general, it is very fast, and only a max function. So it's computationally very fast. That's why efficient. That's why people prefer it. I don't want to just name this vanishing of gradient if you are not aware about the neural networks, and we'll discuss later. But remember these terms also in your mind, right? Remember this vanishing of gradient. So it is, even in layman we can say, as we move forward, as earlier I mentioned, the number of layers, hidden layers, is not a one. It usually a set of layers. So as we move forward or deeper, so because these sigmoids and these functions are range bound between 0 to 1 or between minus to 1. So every time we take a derivative, so these value will reduce by half, approximately by half. So let's just visualize the things. Every time you are computing the value of that, taking a derivatives, putting these values, and this function is range bound. So after 20, 30, 50, it will just near to 0, right? So we call it vanishing of gradient. So when we compute the gradient is going gradually smaller and smaller and near to 0. So whatever the input we pass, however it would be, how large it would be, but final output would be near to 0. That situation is called as the vanishing of gradient, right? Because our function is not giving the output as we are expecting, and behaving in some like constant forms. So that is also one of the reason sigmoid is now less preferred as compared to the ReLU functions. As we can see, ReLU is no foundation on that, so it has less prone to vanishing of gradient function. Similar, softmax is a multi-purpose function. It's not just the activation function. The formula you can see, and it's more like the sigmoid, but slightly better. But it used in the objective function as well when we try to perform the multi-class classification things, right? So if we put the value we have previously calculated or computed after the convolution, these values, convolution 323 2333, if we put in these functions, different function, we will get this. So as we can see in there is no negative values. So if we apply the value, it will be the same. But if we will apply these functions, so as you can see, all the values bit less than 1, right, and greater than 0. So all these values are range bound. Similar in the softmax as well, because we are dividing by this summation over exponential of xi. So it will also the range bound function between 0 to 1, right? So the few special cases and effect of that. So it's, if we apply the sigmoid of that image after the convolution, you will see it's like a blackout, right? Because the value is between the, it's not an exact picture. Most of them, even it's hard to see, because very few values pass that threshold, and that's why it's like seems like or look like a more black, correct? So if we closely observe these image, so there are very few feature, those are highlighted after applying the sigmoid function. If we apply the ReLU, you can see slightly more because it's not impacting much. So what we applying the after convolution, It will just highlighting the edges, so we get more features, but it's like in the dull forms. So that is the application. These are not exact images, by the way, I tell you. These are just a schematic diagrams, or we can say the examples. What is the difference between after applying the ReLU or this, right? Otherwise, mathematically, you see the value of this after applying this, these are the exact values, right? These are the just the examples or samples, to show the effect of these different activation function. So there are others uh, activation function as well. 10h you can explore. It is nothing like a softmax function. It is just a e to the power x minus e to the power x minus x divided by summation of that, correct? E to the power x plus e to the power minus x, I think, correct? So you can see it just a slight different function, and it has been used in many operate, or we can say the many CNNs, especially RNN, which we called recurrent neural networks. So 10h is quite popular in that. And as I earlier explained this softmax, it will use in multi class classification problem, right? As a objective function, as a activation function as well. So this is, just try to summarize these things. So as we can see, sigmoid assay prone to, vanishing of gradient, is smooth, interpretable, differentiable, all these three major characteristics. And it can also be used in binary classification, right? Because it has a clear-cut threshold value. If the value of sigmoid after applying the sigmoid, it's greater than 1, we can, classify as class 1 or whatever. And if it is less than 1, we can classify to the other class, right? So it can also be used, just define the threshold, and you can use as a binary classification function as well. 10h, as I mentioned, it is quite popular in recurrent neural networks and in the hidden neurons pattern learning as well. But as it is also the range bound function, because as we can see, it's always lie in between 0 to 1. That's why it is also prone to the vanishing of gradient problem, right? Linear ReLU, as I mentioned, it's a linear function. If it is the value is positive, so it has fast in computation, avoid vanishing of gradient. But that neuron is stuck at 0, as I mentioned. That's why I introduced the leakage and all. Leaky ReLU, ELU variants of ReLU is introduced to overcome these dead neurons problem. But when we introduce this slight change, these are also adding some computation burden over this, in our CNNs. Softmax we already discussed. Till here, if anyone has questions or doubts or bonding around these activations functions. So here I mention only and discuss 4-5 functions, but 10 popular functions are 10 to 12. Others, other activation function you can explore. Yes, anyone has any query,
Sir,
questions?
is there any limitations for activation function?
Limitations?
Yeah.
Yeah,
We are not supposed to use this kind of functions beyond activation function like that.
Yes. As I mentioned, right? Okay. So in activation, if you see that, right, we preferred actually. So first it would be a non-linearity, correct?
Yes.
Linear function does not make any sense, correct? Otherwise it will be a function. Second is, we preferred it will be a continuous and differentiable, right? And range and domain should cover according to our application. So especially the domain of the function, activation function, right? And third point, as we see the cones, right? In these, initially sigmoid are quite popular, but later we got to know when we have a computation in the latest time, right? And we apply this and try to, initially what happened, people think if we increase the number of layers, right, networks, hidden layers, we will get more accurate answer. But it has been observed after increasing the layer, let's say above 60 or 70s, performance, uh, has been started degrading in that case. That's why people got to know कि vanishing gradient is the issue. That's why they name it after observing that limitation of that. So these are the 4 5 characteristics which we want to keep remain, right? Keep maintain in any activation function. Otherwise, any non-linear function you can use in your networks. And
Okay.
with the time, there are many. As I mentioned, initially people are just happy with sigmoid 10H. Relu is quite, new, recently updated function. Switch this as well also introduced in just like in 2021, right? I didn't discuss here because it will be like more mathematics and more deeper things. We have to cover. We have to cover at least a full CNN in this discussion, right? So leakage is quite new. Yeah, I think in 18, 17, 18 it has been introduced, right? So you can also build or drive your activation function, but should maintain 4 5 these mathematical characteristics.
Okay. Thank you, sir. Thank you.
Yeah. Anyone else or more?
Sir, can we say that every activation function has different use cases?
Different use cases in which respect you are talking about? Yeah.
It's particularly as some of the examples in previous slide you have mentioned
Hmm.
that in spam detection we can use sigmoid, such like that.
No, actually, yeah, thing is that this is just an example of binary spam or not spam, right? So binary classification. Second, we definitely should keep in mind what kind of feature we are looking for, right? So let's say we targeting to detect the small object and a larger object as well, correct? So in that case, what would be the combination of our activation function? So definitely based on the use case, our selection of these activation function make a difference, right? That's why as I mentioned, the Swedish and one more activation function as well introduced for a very specific use cases. Like if we are applying the object detection, in that case, what matters to us, what would be the shape of object, right? We are looking to extract those features. So in that case, activation function would be different, right?
Okay, sir. Thank you.
Yeah. So selection of activation based on the use case definitely matters, right? Will affect the performance as well. So in this slide, whatever I mentioned is just like a thumb rule, like a popular, the things. If you want to go in more deeper in that direction, you definitely affect and can explore the specific things. If you give me the specific examples and want to the specific task, then we'll discuss regarding that, yeah, later. Anyone has any questions or query or discussion, or shall we move forward? Okay. So this is very again, if you see, all the operations are quite simple, right? Pooling is one of the simplest operation in CNN and mathematically, but it impact again has quite critical, also impact the performance of the complete model. So you can see it's the simplest kind of operation. We have the results of using ReLU. First we apply the convolution on this, and then we apply the ReLU, and finally we get this result. If you remember, right? 3 2 3 3 2 3 3 and this. So pooling is simply, as its name suggests, we simply take it, right? consider the grid from the output of the previous operations, usually a convolution and activation function, right? We select a set of these. Let's say here we are applying the pooling of 2 by 2, strike with 1. So what we say, we select first 2 by 2 grid from the output, right, from this matrix, and just select the max of that. That is called a max pooling. Means we are just pull out the maximum of that grid. So if you see the first grid is 3 2 and 2 3. So what would be the max of this is 3. So we just keep 3. Then slide by 1. So our grid would be 2 3 3 3, right? Then if we similarly move down as well, so we will get the 3 into 3 into 3 into 3, right? Everything is 3 3 3. That is called a max pooling. Similarly, and you see the difference. This is again a schematic diagrams, but it is quite replicated near to the actual one. But to visualize and to depict the clear cut the operations, we highlight this slight more actually, right? So you see after applying this, we have this edges is visible but not too bright. After applying this pooling, so everything we make it 3 3 3. That's why now you can see it's quite brighter as compared to the operations, right? Next pooling is, so everyone got this idea of this pooling. We extract the dominant region from that particular matrices and just taking the maximum of the pixels, right? So again, the size usually we apply 2 by 2, because if we see height and width, we will keep it low. If we apply on the full matrix, we will get just 1 pixel, 3, correct? So we usually have 2 by 2 or 3 by 3 max pooling to highlight that region as well. So if it is that small part of the image is important, it will be highlighted. If it is not important, it will be remain same, right? So that's the whole idea about applying this pooling.
दीपक
Similarly,
जी,
yeah,
आपकी जो प्रीवियस स्लाइड पे जाइए एक सेकंड.
yeah, sure.
ये सर, आपको नहीं लगता इसमें जो आपने इमेज दिखाई है नीचे पूलिंग के, उसका साइज थोड़ा छोटा होना चाहिए था?
Oh, okay. No, that's why I mentioned. Okay, you are right. Uh, These are the whatever I have written here mathematically, right? So you have see 3 3 3 3, correct? Right? So you are absolutely right. This size is decreases, right? Only out of 3 by 3 we get a 2 by 2 matrix. This image is schematic diagrams, so it will not image. This right side image is not representing this 3 by 3, sir. Are you getting my point?
हाँ, बट आई थॉट कि उस इमेज को थोड़ा छोटा करके हम दिखा दें तो इट विल गिव यू अ क्लियर पिक्चर.
No.
आफ्टर
I
पूलिंग
tell you.
साइज गेट रिड्यूस्ड.
No, sir. If we will reduce the size of the image, it will not the case actually, right? Size of the image would be the same, correct? The value in that would be reduces or highlighted. If we see, size would keep maintained through the padding as well. Here the purpose of pooling is highlighting the features.
That's right. Even in
Yeah.
the padding, the as corner edges value will not be the value of the image as such, no? You'll be
Correct,
filling
correct.
it some zero value or something else so that mathematically the size remains same.
Yeah, absolutely. No. When we put this 0, right, and we apply all these functions, so it will be keeping into this. If we directly applying the padding after the operation, then it will be black, correct? If we are applying before that, it will be adjusting in that, right? Second, I am just depicting, as I say, schematic diagrams of highlighting this. If we reduce, okay, we can reduce the image, not an issue, correct? But If we reduce here, this image is not the result of only a single operation. But you are right, for more clarity visually as well, we can reduce. Okay, the size is also reducing after applying the pooling, which is the case. Size is reducing, correct?
Yeah, fine.
Yeah. Yeah. So like similar also, if we take the average pooling, that's why in a different case, we take a different kind of pooling operations. In previously, if we want to highlight a particular region, we go with the max pooling. Average pooling is usually used to generalize, generally smoothing the shape of the things, or the image or edges, smooth out the edges or corners. So in that case, especially max pooling is useful in the object detection, usually used in most of the cases. But if we are want to drive, or we can say the develop the network backbone, especially, which can helpful to extract the general features from the image. In that case, average pooling is very useful. So if we go in that mobile network, lighter networks, they use the global average pooling, means extract all the features and average out those to generate the general features. So in that case, it is quite useful, right? So these two different use cases, and the choices of the pooling depends on the application. But in general, these two different use cases. If we see nothing but in the top of the image, we can see the clear cut and the shape and corner. If we apply average pooling, it is just smooth out. So the edges and corners and bright part is like more smooth kind of thing, right? So this is the effect or resultant of this average pooling. If anyone has question related to that, so please ask. So pooling is three popular things: max pooling, average pooling, size may be varied, and the third one is global max pooling. And as I mentioned earlier, right? In global max pooling, we will take a more size of the pooling selection, the area we can say, correct, and take off that. So as earlier I explained, if we take the full image 3 by 3, finally it will be just a 1 point, as uh, in the, sir asked the questions. So in that case, sir, it would be just a point, correct? So from that area only, correct? Global average, if we take the average of this 3 by 3 matrices, it would be 2.3. So this is just an diagram, the value of this, how this max pooling or max average pooling is work in that case, right? So mathematically, even we discuss and it's a simple operation. So what would be the final size of the images? We have the height and size h and w of image before applying the pooling, and it would be the size after applying the convolution and activation function. So we can see the final size would be of the pooling is what would be the size of the pooling area which we are selecting, correct? So if the image is 3 and the pooling filter size is 2, so stride is 1, and as you were asking, sir, here we have taken the padding is 1, so final size would be 2. Effective size after applying the pooling is 2, and height and width both 2 by 2, right? If we note adding the padding and stride would be 2, then because it is in the denominator, it will directly 2 minus 3 1 by 2, so it will become 1.5 or something, but we keep it integer, so it will be 1 in that cases. So simply apply this formula, it is pretty straightforward. Or if anyone has any question, so can explain, but it's quite straightforward, right? We'll move forward, or okay. So this is just I have this slide to show the full picture of how we will apply that, right? So this is the input image, and this is x stride by how this filter, we have taken this filter and how it will move, or we can say apply full image, and what would be the output of that. Correct? So please, stride I usually didn't explain here, but it is very useful, by which step we are moving forward. So in the convolution as well as in the pooling, everywhere you see the stride, right? So if stride is 1, we are moving one step right and one step down, right? One step means by one row or by one column, move forward or downward. Correct? If we take a stride 2, then we start moving rightward or downward by 2, actually 2 column or 2 row, right? So that's why this everywhere, please keep in mind, it is in denominator, directly reduce size by whatever you have taken, right? And it's very important when we extracting the features from the data, right? So if it is clear till here, then we'll move to the flatten layer. So flatten nothing but whatever the output we get after applying the pooling, right? So now initially we are using the CNN. Now we are trying to convert into the ANN. So everyone is aware about the ANN. So what we get output is 2 by 2, or it could be 250 by 250. It could be 128 by 128. I usually take the power of 2 to the power n, because features and everything we have considered in 2 to the power n. So here the output is 2 to the power 1, 2 by 2. We just simply try to flatten out. Flatten out nothing but just 3, 3, 3. This is not a good example, but it simply start from the left top corners and just start putting these value, right? So 0, 0, 0, 1, 1, 0, and 1, 1. Simply flatten out. This is called a flatten layer. This will use to finally applying the operation, whatever the classification, object detection, and whatever application, finally your objective would be, we will apply this. So straightforward, and simply as we have discussed in the ANN, it is a fully connected layers. So every input is connected with every neurons, is called a fully connected. So first flatten out the layer, then connect with each and every neurons. So it is pretty, it's completely similar to the ANN fully connected layer. Correct? So finally is as we saw the first slide diagram objective function. So I just give the glimpse, and more we will discuss in the tomorrow discussion in classification and all. So finally, till now, whatever we have discuss around this, what we want to do, right? Classification, object detections, segmentation, so many tasks we can perform using CNN. So what would be your output function? It is straightforward, like as we apply in any machine learning function or any SBM, regression, neural networks. These are similar to that. The only difference is because we are applying for images or or video or vision part, so the value will slightly change. But as we can see, the loss function is simple, straightforward. What would be our predicted output? Y dash. What is our actual output? Y, I represented by this. And we simply try to compute the difference between these two, values, true value and predicted values. So in classification, as we know, we try some numbers, and in regression, we try the difference between that. So state mean square error is popular, loss function value. Similar function is used in CNN as well. Whenever we use a regression objective function, or we want to find out the difference between the actual numbers, right? Second problem is related to like a classification, multi-class classification. So in binary, we simply use the cross entropy, two-class cross entropy, or the sigmoid function. And in the multi-class, we can use the categorical cross entropy function or the softmax functions as well in the combination of that. So these are pretty straightforward, loss function as we use in the other ANN or other machine learning or AI algorithms as well. If someone has a specific doubt related to that, please ask, and we can discuss around that, right? This slide I have just added if someone interested, because this slide will share with you, so he or she can explore around that also. Or otherwise, if we will get time tomorrow, we'll discuss in combination with the classification and object detection problem. Yeah, so till now actually it is related to the CNN part. So I want to stop here. If someone has the question related to that, please ask.
No, sir.
Okay. So can we stop here, right?
So, is there any question from participant side? Okay. So, I think there is no question. If we have some questions, then we will share those sessions with you through email, sir. Okay.
Thank you. Yeah. Thank you so much.
So, thank you, sir, for the insightful talk. The session provided a comprehensive understanding of artificial neural networks and highlighted the need for convolution neural networks. It further explained the underlying mechanics, mathematical foundations of convolution, and architecture of CNN2, along with the role of activation functions and pooling layer. So we sincerely thank sir for sharing your valuable knowledge, time, and expertise, which has greatly enriched our understanding of the subject. So thank you, and hope we will meet again. I think in tomorrow's session. Okay. So
Yeah,
thank you very much.
Yeah. Have patience and shown patience to listen me, because I try to cover whole this, which is not actually a good, possible actually. So
I think
I just
Dr.
touch
Ankur
the
wants
point.
to say something. Dr. Ankur?
Yes, sir. Good evening.
Good evening.
Okay.
Sir, actually, I wanted to know that as per my knowledge till now, matlab, CNN and these neural network architectures we are using to optimize our models, mathematical models, means we have to work on our models only, and then we can utilize this to get the optimized output. So, if we want to do research on CNN, so what are the mathematical aspects that I wanted to know, sir? Inside the architecture of CNN and all.
Okay. So yeah, really good question. Thank you so much, Ankur, asking this. Actually, if you see, and I mentioned so many time in between the this discussion as well, right? So it seems as simple operations, right? Everything is simple, right? But if you see and start exploring the CNN, the research as well as the beauty lies in the architectures whole. So if we see the one pair of these operations, these look or seem simple, but how you combined, right, and see the effect on that. So lot of research and thousands of different architecture means more than 50 I have gone through the popular architectures. And so that is the one area, how you drive your backbone of that, correct? Like the most popular yesterday, tomorrow we'll discuss related to the YOLO and how the performance is different. So that is one aspect. You can work and we can explore and do the research and experimentation around this whole backbone and architectures, right? Second is, as I mentioned in between, like activation function is one, what kernels we are using. So lot of it limited in compared to the other AI field, but it is very useful. How we are connecting these points and how many layers we are using, that is one aspect. Second is what mathematical functions we are using, like activation function recently also, and in different use cases, different activation function. Second, I just touch and miss that how we are collecting, storing, and extracting the features. So there are also a different, way. I didn't go in that detail in today discussion, right? If tomorrow we'll do that. How these features, climate feature selections, how we are keeping those features. That is the another mathematical area as well to use the CNN and do the research and exploring the new aspect related to the CNN, especially in the mathematical sides, right?
Right, sir. Thanks a lot, sir.
Yeah.
Okay, so any other query? We can consider one more if it is there.